So after an introduction of what is a limit, then we come up with our techniques for finding limits, right? And, you know, there's a finite set of techniques that we use to do this with, one of which you've actually already done, direct substitution, and then we learn about the others after that. Right? These are the methods that we use for evaluating limits. And the number one was direct substitution. Last year, in the book we used up till last year, that orange book over there, they actually started this section by talking about direct substitution. They had already talked about it in 12.1, and then they redid it at the beginning of 12.2. This time they took it out. It's not in there at all. Right? The thing about direct substitution is we're going to use direct substitution on almost all of these. It's always what you try first. Right? Direct substitution means if you're taking the limit, right, as x approaches c of f of x, right, you plug in c. If it works, there's your limit. As long as it's the same from both sides. So direct substitution we'll use, but it's been presented already. Then dividing out, which is basically means factoring. Rationalizing is a very particular technique. Graphing. Graphing's kind of important because there's some limits that we can't get at algebraically, but graphing, it helps us. And one-sided limits, we kind of already talked about that. What they talk about here is not any different than what we already talked about, limits approaching from different values from the opposite sides. So dividing out technique, right? The limit as x approaches -3 of this here. The first thing you try is direct substitution. Plug in x equals -3 into the numerator and denominator, and what do you get? Right? So let me do that over here. Direct substitution. Right, I'm going to get -3 squared plus -3 minus 6 divided by -3 plus 3. Okay, so in the numerator, the -3 squared is +9. Minus 3 minus 6 is 0. Denominator, -3 plus 3 is 0. Okay, so direct substitution doesn't work because we don't know what to do with 0 over 0. 0 over 0 has a name. That's called indeterminate form. Right? 0 over 0 is indeterminate form. You know, but because both the numerator and the denominator are polynomials, you know, what it means is you can divide out the 0 and then see what's left. It's easy to see this x plus 3, right? I mean, there's nothing to factor anything there. But the fact that you were able to substitute x equals -3 here and get a numerator equals 0 means x plus 3 must be a factor. And we could see that because x squared plus 6 minus x is a pretty simple factoring problem, right? The factors of -6 that add up to +1. X plus 3 times x minus 2. Right? And so this is the limit as x approaches -3 of x plus 3 times x minus 2 over x plus 3. Right? Because we got the indeterminate form, we knew both the numerator and denominator had to have a factor of x minus -3 or x plus 3. So we factored it. And now we can cancel. Right? That's dividing out technique. So now we're taking the limit as x approaches -3 of x minus 2. Okay, now try direct substitution again. What do you get if you've tried direct substitution here? -3 minus 2 is -5. So actually, we can do it now. So you start with direct substitution. You got an indeterminate form. So you factored the numerator and denominator. You divided out the common factor. And then you do direct substitution again, right? This is -3 minus 2 equals -5. Right. Now, if you graph this, I probably have this open anyways, so I think I'll go there. If I graph this, is that already on the next section? What am I doing? Oh, these are the exercises. Oh, did they not do the graph? Okay, they didn't do the graph. If I graph it, you know, the function is going to look like y equals x minus 2, right? If I look at the graph of y equals x minus 2, that's a straight line. It has a y-intercept of -2. It has a slope of 1. So it looks something like this, right? But at x equals -3, 1, 2, 3, you would go down here and there would actually be a hole in the graph, right? It's not actually defined. This function here is not defined at x equals -3. There is a hole in the graph. But if I was going to take the limit, as we learned in the last section, from the left and the right, it does look like it is approaching the same number, right? Now, I can't tell what that number is by plugging it into that. But after I've divided out the common factor, I can. It looks like it's approaching the number -5. At x equals -3, it looks like it's -5. That's actually a hole in the graph. Okay. So dividing out technique. I think we have one more. Dividing out technique. Again, first step, try direct substitution. What do you get? Direct substitution, meaning plug in 1 for x here, 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 or not here, 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 here. In the numerator, 1 minus 1 is 0. In denominator, 1 minus 1 plus 1 minus 1, 0. 0 over 0, right? That's indeterminate form. Okay, what does it mean? I mean, we know that 1 is a 0 in the numerator because there's only, it's a linear factor. But what it means is that x minus 1 must be a factor of the denominator too. It has to be. We just have to figure out, well, what would be left if we divided this polynomial by that. So how could we figure out the factoring of that? What's that? Yeah, I mean, when you have 4 terms, you could think of it as factor by group. You should always just say factor by grouping. Think of what would happen if I grouped the first 2 and the last 2. Now, another thing you could do synthetic division. You could do polynomial long division. You know, in some way, you got to divide that by that. If you do it by grouping the first 2 and grouping the last 2, right? This is going to be the limit as x approaches 1 of x minus 1. And then the first set of parentheses has a common factor of x squared. And what's left if I factor out the x squared? X minus 1 plus x minus 1. So this is the limit as x approaches 1 of x minus 1 divided by x minus 1 times x squared plus 1. That was bad. Okay, so now we've got the common factor. Right? You could have gotten it a different way. Let's say you could have just divided this by this. But in the end, we factored it, and now we see the common factor, so we cancel it. So now we've got this. The limit as x approaches 1 of 1 over x squared plus 1. So after dividing out the factor, direct substitution again. What do we get if we do direct substitution here? It's going to be 1/2, right? So check it again, and if you can, then that's 1 over 1 squared plus 1, which is 1/2. So the limit equals 1/2. Right? The function would have a graph that looks like this, except that it would have a hole at x equals 1. Right? There would be a hole in the graph. So that's dividing out technique. Rationalizing technique. You know, right away when it says rationalizing, that probably means that there's something irrational about the function, right? Which means square roots. I mean, when have we used this before? Rationalizing denominators. Usually that's what you do, is you've got a square root in the denominator and you're trying to do something to get rid of it. So you rationalize. And do you remember, if this was a denominator and we had to get rid of the square root in the denominator, what would we have multiplied by? The conjugate, right? If that's the conjugate of the numerator would be the square root of x plus 1 plus 1, right? It's what you get if you just change the sign in between them. Remember, when we were rationalizing denominators, it had more than one term. It was always with a square root. Then the strategy was to multiply by the conjugate, not by the denominator divided by itself. That's if it's just one term, right? So in this here, the rationalizing is going to be multiply by conjugate. And conjugate of what? The conjugate is a numerator. You know, the one that's got the irrational in it, the square root. So let's do that. So that would look like this here. The square root of x plus 1 plus 1. But if you multiply it in the numerator, you got to multiply it in the denominator. Okay, so first step, multiply by conjugate, divided by itself. Okay, what you don't want to do at this point, don't simplify the denominator. Leave it like it is right now. There's going to be some cancellation that'll happen, and it'll happen easier if you haven't already distributed that x. Okay, so don't do that yet. Foil the numerator. I mean, you remember, the reason why we multiply by a conjugate is that you really don't have to foil, because the middle terms will always cancel each other out. The fact that these two, that these have opposite signs, right? The middle terms are going to be the square root of x plus 1 times positive 1, and the square root of x plus 1 times negative 1. And when you add them up, they cancel. So you really don't have to multiply all 4 terms in the FOIL. You just got to do the first terms and the last terms, right? So we're not doing FOIL. We're just going to go the square root of x plus 1 times the square root of x plus 1 is x plus 1. And minus 1 times 1. Right, and again, I didn't simplify the denominator, I just left it like it is. Because when I simplify the numerator, the 1's cancel, And all I'm left with is x. And x, because I didn't already distribute it, is clearly a factor of the denominator. I'm going to be able to cancel that. Right? See the x factor, cancel. The limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now, you know what I didn't do at the beginning, which I should have done? Try direct substitution. I mean, notice if we would have tried to plug in 0 here, we would have gotten indeterminate form, right? Because you would have had the square root of 1 minus 1 in the numerator, and you would have had 0 in the denominator. So it would have been 0 over 0, right? After you've done the rationalizing technique, again, you're going to do direct substitution. What will we get if we plug in a 0 here? What is it? What's that? I know, but what's the whole thing equal? 1/2, right? That's going to be 1 over the square root of 1 plus 1, which is 1/2. Right? So the limit is 1/2. But whenever you see this square root, you're going to be doing this rationalizing technique. Multiply by conjugate. See if there's another one. Okay, approximating a limit graphically, which means, we're going to put in the calculator, look at the graph. What would we get if we tried to do direct substitution at the beginning here? If I plug in a 0 for x here and here, what do I get? It's an indeterminate form, right? This thing does not have a value at x equals 0. So then we look and see, well, what does it look like on the calculator? And so let me go over here. Clear. Y equals clear. Sin x divided by x. Okay, if I look at the graph, it's just going to be whatever zoom it is. Hopefully it'll look like something. It's kind of hard to see. I can zoom in. If you have trouble seeing that, you can zoom in, zoom to. So what we know is at x equals 0, this thing does not have a value. In fact, look at the table of values. I'm too high. Right? At x equals 0, it's an error. But does it look like it's approaching a number? Let me do this. Let me go with let me do this. Table set. Let me set it to ask. So we get the same kind of table of values that they would. Second table. Right? And let's see what happens if I go 0.1. I'm approaching from the right. 0.998. How about 0.01? 0.99998. 0.001. And now it's just rounded. I think if I went over into the margin, it's actually 0.9999999. Did kind of tell what it's approaching? It looks like it's approaching 1. So let's go with negative numbers. Negative 0.1. Negative 0.01. Negative 0.001. So what does it look like it's approaching from both the left and the right? It's approaching 1. So, we don't have a technique, an algebraic technique like we just went over to handle that, but we can see it by looking at the graph. Okay. So that's the graphically, what was the last one? One-sided limits, right? We talked about this last class, right? And I've just reprinted the whole example, but the classic example of when a limit doesn't exist is when they give you a function which is an absolute value divided by something that's not an absolute value, right? Because the absolute value in the numerator will always be positive, but the one in the denominator is going to switch signs, which means that what you're looking at on the graph will be positive at one part of the domain and negative at another part of the domain. So if we had to find the limit, we would have to take the limit from the left and the limit from the right. Right? One-sided limits, the way you write that is the limit as x approaches c, and this little superscript of a minus means it's from the left. Right? This thing right there means from the left. And if you put a plus on it, that means that it's from the right. Now, what did they ask here? They asked us to find the limit from the left and the limit from the right. Right? So we can write that. The limit as x approaches 0 from the left equals what? Look at the graph. What is the value of the function for every value to the left of 0? It's -2. Right? And then we can do the right-handed limit. And we would say +2. Now, they didn't actually ask us, does the limit exist? Right? They just asked us for the left-handed and the right-handed limit. Okay, there they are. Now, if they ask us, the next question is there a limit as x approaches 0 of this function? You would say no, because these have to be equal in order to have a limit, and they're not. So I don't think there's much new in that we didn't already talk about, other than they did officially give us that notation of the minus and the plus. Now, the other place that you can see this come up will be in the next. We're done? Okay. Well, this is just the reemphasize. The existence of a limit, f is a function and c and l are real numbers, then the limit as x approaches c of f of x equals L if and only if both the left and right-hand limits exist and are equal. So that would be an example of not being equal. That's exactly what we did in the last class. Okay. So we could also see the same kind of thing remember what we call this? The piecewise function, right? In a piecewise function, you use a different function on different parts of the domain, right? You get the function, the expression, which is the function, and then you get the domain you're supposed to sketch it over, right? And then it's the expression and the domain. Now notice in this, in this piecewise function, we're using 4 minus x for x less than 1. We're using 4x minus x squared for x greater than 1. What did they leave out? There's no 0, right? Which is why when you look at the graph, there's an open circle at x equals 1. The function is not defined at 1. Not because there's any kind of divide by zeros or anything. They just didn't define it at x equals 1. So there's an open circle. Now, if I'm going to find the limit of the f of x, right? If I'm finding the limit from the left, I'm following the line. Now it's not a straight horizontal line, which every point is the same, every y value is the same, right? It's changing, but we can see the trend, right? If we were able to keep going until we got to x equals 1, it looks like we'd be right there, right? Which is 3. And if I did a right-handed limit, right, I'd be coming around this side, and it looks like it's pointing in the same place at 3. So the left-handed limit, right, is 3. The right-handed limit is 3. And so the limit is 3, which you can get that, just plug in 1 here and here. See what you get. Right? If I plug in a 1 there, 4 minus 1, 3. Plug in a 1 there, 4 minus 1, 3. So that's going to be the limit. Right? The limit as x approaches 1 from the left equals 3. The limit as x approaches 1 from the right is 3. And therefore, the limit as x approaches 1 of f of x equals 3. Again, you know that by plugging in the 1 here and here. You can figure out what value it's going to be. I mean, this graph is pretty clear just looking at the graph. But I think I have one more like that. Good. Okay, so here's another one. Find the limit of f of x as x approaches negative 1. And again, they've defined it in 2 different expressions covering 2 different parts of the domain, less than negative 1, greater than negative 1, but not at negative 1. Okay, now if this thing is going to have a limit, these both better be pointing to the same point. So before we get started, let's just plug in x equals negative 1 in both expressions and see what we get. Right? For the first expression, right, we're going to get negative 1 squared minus 3 times negative 1, which is going to be negative 1 plus 3 is 2. Right, for the second expression, we're going to get negative, I thought that didn't work. Make sure I'm doing the right thing here. Negative 1 plus 3 is 2. Okay, it does actually point to the same thing. Right, so, you know, in the end, we could sketch these graphs, right? That one is going to be a straight line. Y-intercept is 3, slope is 1. That one is going to be a parabola, opens down. They're both going to be pointing at the same y value, even though it's not actually defined in the function. We can say that the limit as x approaches negative 1 of f of x equals 2. So just, you know, evaluate the function for both expressions at that value. If they're pointing to the same place, that's the limit. If they're not, then there's no limit. So that's the first lesson, right? So we did direct substitution, we did dividing out technique, rationalizing technique, graphically. When they say graphically and numerically, we went to the table of values, right? And then the one-sided limit. And that is the homework, which you need to work on now. We'll see. I mean, I would hope by 10 or so that we're done, but you know, we have time. What's that? No, that's a comma.